All right, so we're going to look at the angle between two planes. So basically, in three dimensions, you can be given two planes. I think you would agree that there would be an angle that you could find between those two planes. So that's what we're going to look at today. Here's all the information. If you want to pause the video and have a read, otherwise, we're going to step through it step by step and hopefully make some sense of it. So let's do that. We first say that the angle between two planes equals the angle between two normal vectors to the plane n1 and n2. So you can think about it like this. The normal vector of the plane sort of tells you the orientation of the plane in space. So if you have the two normal vectors to each plane, then you've basically got the direction in which the plane is facing. And then if you find the angle between those two normal vectors, it will tell you the angle between the two planes. Now, there's a bit more to it, so we'll step through that. So first thing just to say is to recall that, you've got some Cartesian equation, a1x plus b1y plus c1z equals k1. I'm going to use this green plane here to represent that. First sort of plane in space, and then we've got a2x plus b2y plus c2z equals k2, sort of our blue plane that we've got going on here. And recall as well that we know, so actually, firstly, let's say this. We know that these planes in two-dimensional space, if two lines intersect, they intersect at one point. In three-dimensional space, if two planes intersect, I think you would agree that they would intersect on some line. So what we have here is the line on which those two planes intersect. And what we've also put on there is just some point P. Now that point P can be anywhere, just sort of arbitrary at the moment, but we can sort of shift that up and down. Like point P is just some point on the intersection between the two planes, so it lies somewhere on that line. And I suppose what we're going to say is, let's think about some normal vectors to these planes. Now, hopefully from another video, you can recall that the normal vector to the plane can be given by the position vector that's equal to the coefficients of each term. So A1, B1, C1, position vector that points at that coordinate will be normal to the green plane in this case. So that's sort of what we got here, but it's obviously starting at the point P. Okay, so we've started our position vector at the point P, and it's sort of pointing, in that direction in this case, which is perpendicular to the green plane. And then we've got N2, right? So N2 is again the coefficients of the second plane, A2, B2, C2, and starting at the point P. And sort of what we're claiming in this video is that the angle between these two vectors is equal to the angle between the plane. So if we sort of get a good look at this, get it lined up, you can sort of see basically that this angle in here is going to be equal to the angle between the plane. Now, that to me wasn't immediately obvious, and believe it or not, this is for me for some reason been the hardest part of making this. Is I haven't been able to prove algebraically that this angle. In fact, we can put the angle in. That angle there is equal to the angle between the plane. It's sort of obvious in some sense, again, because you're given the orientations of the plane. So the angle between the vectors should be the angle between the plane, but in any case, this is the best I could do in terms of saying, all right, this angle theta, if we just sort of think in two dimensions now, we've got our green plane here represented in two dimensions and our blue plane. This angle theta is the angle between the two vectors that are perpendicular to their respective planes. And then I suppose as we rotate theta around, we can see that it's equal to alpha, where alpha here represents the angle between the two planes. So I'll just sort of show you what I mean. That sort of angle there just gets kept. So that theta angle gets kept there. I'm just having a brain blank in terms of why theta equals alpha, but I feel like it's hopefully intuitive enough that they equal each other. But I would love to see someone comment on why the algebraic reason why theta equals alpha here. I feel like it's obvious. I'm just missing something that I can't think of right now. So in any case, we know that this angle theta is equal to the angle between the planes. And so the last thing we're going to say is sometimes the angle between the vectors will be greater than 90 degrees. So I suppose conventionally we say that it's the angle that's acute. So if you do get an angle for theta that is greater than 90, you have to do 180 minus theta, which will just give you the acute angle, because that's the one we're interested in. We're interested in angles in the interval between 0 degrees and 90 degrees. So yeah, there you go. I think that's a pretty interesting idea. Just to again summarize, angle between two planes is equal to the angle between the two normal vectors to the plane. So yeah, good luck with all your studies, and I will talk to you soon.